But let's see, are we back now? Yes, it's recording again. Okay, so tonight's video will be in two parts again. Yay. No. Okay, so everything looks good now from there?
Yep, we're good.
Okay. See how long it stays that way. Okay, so now the actual algorithm for what's called Gaussian elimination. And the idea there is to reduce A to upper triangular form. Side comment, Gaussian elimination was not developed by Gauss at all. Somehow his name got attached to it. In fact, I believe the earliest known usage of Gaussian elimination, I think dates back to China, like very long time ago. And somehow someone associated Gauss's name with this process, and the name kind of stuck. So I don't remember the details about the history of it, but that's what I learned from it. And it's weird because Gauss had enough things legitimately named after him. He didn't need one more for free. But no one knows who it should be named after. No. Okay. So in terms of like a pseudocode, the algorithm is this. So as I mentioned in the example, we start with column 1. So J is refers to a column. So we're going to start from first column and keep going until we reach column n-1. After column n-1, we don't need to eliminate any more entries. So throughout this, J is going to refer to the column we're currently working on. And I'll put an end statement down here. So everything in between that I'm about to write works on that column. Okay. Now, within that column, I need to go from immediately below the diagonal all the way to the bottom. So I is going to be my row index, as I usually is. So in each column J, I'm going to start with the element directly below the diagonal and keep going down all the way to the bottom. And so we only want to consider each row below the diagonal. Okay. Now, then I'll put an end there. So everything in here is meant to perform a single row operation. The third kind of row operation. Subtracting a multiple of one row from another. Now the first thing is, the idea is we're going to do row I is equal to row equal to itself minus some ratio times row J. This is a row operation that's being performed using a notation that I had over there. But what ratio should we use? So it's going to be the element we want to eliminate, which is Aij, divided by the diagonal entry in the same column. And this is referred to as the multiplier. We have to make sure, of course, that this is non-zero. For now, we're going to assume that it isn't 0. That when it is 0, we have to do what's called pivoting, row interchanges. We'll deal with that later. Probably not today. Okay, so once we have a ratio, now we have to perform the actual row operation. But what does that mean? We're going to go across the row and update each element. So I'm going to use K as a index, a column index within that row. But I only need to update entries in this row starting with column I plus 1, I plus 2, all the way to the end. I don't need to touch Aij because I know what's going to happen to it. It's going to become 0, so I don't need to actually carry that out. That's a waste of time. So in this row operation, what I do is I'm working on a single element. So Aik is equal to itself minus the multiplier times the element in the same column. Notice the column entries match, but row j. So this loop here actually updates all the entries in row I that need to be updated. All entries prior to column I plus 1 are going to be 0. There's no need to touch them.
Okay.
Yeah.
You said column I plus 1? I thought our J's are columns.
Well, J is the column we're working on to figure out which entry to eliminate and how to eliminate it. But once we carry out the row operation and to eliminate Aij, so Aij is going away. But the rest of the row is affected by that, and that's what this handles.
So should that, in the note, should that be K equals I plus 1 and I plus 2 then?
Oh.
You have J. And that's, so is that wrong then?
The notes are right.
Okay, that's what I was wondering.
Yeah.
Shifting.
Yeah. Yeah, that would have been wrong. So, yeah, so everything from column J onward needs to be updated. I just got back from break like all of you. Okay. Okay. Actually, I'd rather I be wrong than the notes wrong. If the notes are wrong, then there's more chaos. But sometimes they are wrong. Okay. So now that we've finished dealing with the row of the matrix, we also had to perform a row operation on the right-hand side values, that last column in the augmented matrix. So we just handle that down here. So we're working on row I still. So Bi is equal to Bi minus the same multiplier, the same row operation, times Bj. So row I is still row I minus the multiplier times row j. So that applies to the matrix as well as the right-hand side values. Okay. And that's it. That's the whole algorithm for Gaussian elimination that reduces A to upper triangular form, and then applies the corresponding row operations to B. Now, here we're carrying this out for all columns K going from J plus 1 up to N, but I want to show you what happens in column J if we were to do that. So Aij is equal to Aij. So all I'm doing here is I'm setting J equal K minus the multiplier, but the multiplier is Aij over Aij over Ajj times Ajj. And what happens is these cancel, and then these cancel, and we get 0. So that's why the row operation works. That's why this is the correct multiplier for eliminating elements below the diagonal. So we don't actually perform this in the code, but this is just confirming that this is the actual ratio we want. So any questions about this process? So everything I did in the example, this is basically the code for that. Oh, yeah, yeah. Yeah, just because it doesn't depend, because we're using the same ratio throughout this loop. Yeah. So yes, it is a deficiency thing. Actually, if it wasn't done there, the compiler would, if it was done here, compiler would probably move it out anyway.
Really?
Well, I'd like to think it'd be that smart. If it's set to optimize. So, well, maybe worth investigating if any of us have time, but we don't. Okay. Oh, we do have a computer science professor in the room. What do you think? Oh. That if this line was written in here, I don't know if a typical optimization algorithm would be smart enough to actually, like in the generated code, put it here anyway. So, probably some very sophisticated analysis would be able to detect that, but I don't know if a typical optimizing compiler would. Okay. All right. Now, as far as efficiency is concerned, how many operations does this take? So the complexity of this algorithm is order of approximately 2/3 n cubed flops. By flops, I mean floating point operations, additions, subtractions, divisions, multiplications. And it makes sense that the complexity is on the order of n cubed because this is an n by n matrix, and we have 3 levels of loops that can take as many as on the order of n or nearly n iterations each. So because of 3 level loops, we have a cubic algorithm. So this is pretty expensive. It'd be nice to kind of avoid this, but for a general matrix, this is the kind of expense we need to go through. Unless we have certain situations where a lot of the entries are 0, then we can get around that. But for most general case, it is this expensive. But we will see some special cases later on that are of interest in applications, like banded matrices or positive definite matrices, where this complexity can be reduced. Okay. Now, so this is one algorithm we need just to reduce the matrix to upper triangular form. Once that is finished, we still need to carry out substitution to compute the unknowns, to compute the entries of x. So that's a separate algorithm, back substitution, which I'll do now. And hopefully I can move this without dropping a connection again. Okay. Okay, so next we have